So yeah, I really like this this piece. I guess I instantly think about carbon when I look at it. So carbon has a number of different structural forms, which you would call allotropes. One of them is diamond, and another one is graphene. And this looks most like graphene. So graphene is a planar 2D material made entirely of carbon. And carbon can form up to 4 bonds. And what it does in graphene is it forms 3 bonds with all the other carbons around it. So you get this very strong network in a 2D direction. And because it can form 4 bonds in total, and it's only used 3 of those bonds, it has 1 free electron. So for materials to conduct, there needs to be freedom of movement for the electrons. They need to be able to move around and not be held in the same place. So metals, for example, have strong metallic bonds, but they have a free sea of electrons that allow conductivity to happen. And it's the same with graphene. Every single one of the carbons in graphene has 1 free electron, and so it can be conductive. And that's extremely useful for a number of materials, for example in electronics, maybe when we go to Mars, maybe in sort of space type technologies, that sort of thing. You can make these types of 2D planar materials with other elements as well. So carbon sits here on the periodic table, and if you take boron and nitrogen, you can combine them as well. So you can have boron, nitrogen, boron, nitrogen, boron, nitrogen. All starts to sound kind of a bit confusing, but you can get some interesting, again, 2D material type properties. What do I mean by 2D? Obviously most things are 3D, but you can't, with these, it's only going to be an atom thick in one plane. So you could never get anything thinner than that with atoms, basically. So you can have these incredibly thin, very flat surfaces that might have some very interesting electronic properties. So, why is graphene so strong? Why are diamonds so strong? I guess a good way to think about material properties is the particle model. So these things can exist as a solid, liquid or gas, and the differences between all of those physical states is just how close and how tightly held the particles in the state are. So for a solid, they're held right next to each other and they can barely move. For a liquid, they can move past each other a little bit more, but they don't really move. I mean, they can move completely freely, but for a gas, they're just sort of blasting around everywhere. So the strength of a material depends on how easily you can move one particle past another particle. So for diamond, it's super strong because to move any of the particles, which in the case of diamond would be individual carbon atoms, past another one, requires that you break 4 extremely strong carbon-carbon bonds, which is why diamonds are extremely hard. So they can scratch the surfaces of many other things, but you can't scratch diamond's surface. And so what else have we got here? I guess you can have a look at, a lot of things about graphene is that it can be transparent if it's super thin. As you start to stack graphene, it goes back to being something called graphite, which is what you get in old pencils. I think how they used to make cannonballs, all sorts of things like that. Or I think they used to carve out the structures of cannons or something. Look it up in the history books. Anyway, so graphite is layers and layers and layers and layers and layers of graphene. But if you can if you shave off one single layer, which is what they did in the first place, you get graphene. So when it's that thin, it can be super strong and transparent. But as you start to add things to it, it becomes more complicated. I really like the piece. I like the way that you're led into the sort of center of the sphere by this sort of encircling graphene layer. Did you intend it to be graphene, or is that where you got your inspiration from, or?
No, it's a little bit more organic than that.
Okay.
It's just exploring structure and form and repetition and.
So I guess you've got kind of like beehive-y type stuff. You've got plant cell wall, like matrices of plants, that sort of thing. That looks vaguely like a sort of steroid structure, which we can computer add later. I think that is probably it on the piece. Yeah.